If somebody gave you an algebraic expression like x squared plus y plus 4, and they told you that x was equal to 1 and y was equal to 2, then you could work out a numeric value for that expression just by substituting in and combining the numbers that you got with the usual arithmetic operations. Like you would have 1 squared plus 2 plus 4, which is 1 plus 2 plus 4, which is 7. But on the other hand, if you were given a well-formed formula like P implies Q or not R, and somebody told you that, say, P was true and Q was false and R was false, well, you could substitute in those truth values, but you don't yet know how to combine them using the connectives. At the moment, our connectives are just symbols. They don't have any meaning beyond a mark on a piece of paper. Now, there's no law of the universe which tells you what these connectives do, so we have to use a definition. We have to give a definition of how these connectives will combine truth values. That's what we're going to do in this video using truth tables. So to begin with, let's talk about the formal way in which we give truth values to propositional variables, and that's via what is called a truth assignment. So the definition is that a truth assignment for a set V of propositional variables is a function which we'll usually call lowercase v from that set of propositional variables to the set containing true or false. So T and F here just stands for true and false, as usual, as it will throughout Math 5. Don't be put off by this weird vocabulary around functions and things like that. This is a really simple concept. So if we just take as an example, we might take our propositional variables to be just P and Q, and then an example truth assignment would be the one which sent P to true, which we'd write like this, and Q to false. So there's one example truth assignment, and of course there will be several others. In fact, if you've got 2 propositional variables, then there will be 4 different truth assignments, because P could be true or false, and Q could be true or false independently of what P was. So that's 4 combinations in total. So what we're aiming to do then is that given a truth assignment V on a set of propositional variables, what we'd like to do is to use that truth assignment actually to give a sensible truth value to any well-formed formula that uses those variables. And we have to define how we're going to do that. So let me say what I mean by the word sensible here. I mean, obviously you could just decide that all of the well-formed formulas are going to be false, and that's not a particularly helpful or useful thing to do. So we'd like to do this in a meaningful way. So what I mean by that is that when we have the connective and, the meaning that we give to the connective and should correspond to the ordinary English language meaning of the word and. Let's look at that in more detail then. So let's suppose that we have a truth assignment, V, and we've got some well-formed formulas, phi and psi, so this phi and this psi, and that we know somehow the truth value that we're going to give to phi and to psi under this truth assignment. And the question is then, what truth value should we give to the well-formed formula phi and psi? And the answer here is, well, if we're going to do this in a way that reflects the ordinary meaning of the word and, then phi and psi should be true when both phi and psi were true and false in all other cases. That's because normally when somebody says it is Monday and it's raining, the only time that they're telling the truth is if both of those things are true. It is Monday is true and it is raining is true. So we can capture this definition in this thing here, which is the truth table for the connective and. And what the rows of the truth table are saying are as follows. The first row says that if phi and psi are true, then we will regard phi and psi as being true. So this value in the last column is true, and that's saying that when phi and psi are both true, then phi and psi will be defined to be true. And the other rows tell you that in all the other cases, so when psi and phi are both false, for example, that's the bottom row, then we'll regard phi and psi to be false. Or if you look at the second row, that says when phi is true and psi is false, we'll regard phi and psi to be false. So this is how we will define the meaning of the connective and. We'll also use AND in a slightly different way. We're going to use it as a logical operator. And what I mean by a logical operator is a way to take two truth values and combine them into another truth value. So going back to the first slide, you know how to combine two numbers using the symbol plus, right? You can combine 1 plus 2 into the number 3 using the symbol plus, using addition. And we couldn't do that using logical connectives. We didn't know how to combine two truth values using a logical connective. And what we will do is we're going to define a way to combine two truth values into another truth value using the connective AND by just looking at the rows of this truth table. So from the first row of the truth table, we're going to make the definition that when we see true and true, we'll define that to be true. And from the second row of the truth table, true and false, we're going to define that to be false. And all the other ones will be false as well. So false and true will be false, and false and false will be false. So this is what I mean by a logical operator, a way of combining two truth values to get another truth value. And the way we do this is just by looking at the truth table we used when we defined the truth behavior of the connective AND. So we have to do this now for all our other connectives. So let's begin with the connective OR. So here is the truth table we use to give truth values to well-formed formulas which have an OR in them. And of course, the ordinary meaning of the word OR is that if I say A is true or B is true, then I mean that at least one of those things, at least one of A and B is true. So we're going to regard the well-formed formula of phi or psi as being true under a particular truth assignment if at least one of phi and psi was true under that truth assignment. And just as we did for AND, we'll also regard the symbol OR, this wedge symbol, as this V symbol rather, as a way of combining truth values into another truth value, so as a logical operator. So looking at the rows of the truth table for OR, we'll consider true or, let's have a pen back. What am I doing? True, we'll regard true or true as being true. That's the first row of the truth table. And the second row, from the second row, true or false will be regarded as true, and false or true will be regarded to be true. And of course, the last one is the only different one. False or false will be false. So what this is saying is that the only way in which a well-formed formula phi or psi will be false under a truth assignment is when both phi and psi were false under that truth assignment. All right, we'll do a similar thing for the connective NOT. So the truth table for NOT is right here. And what this truth table says is that if you have a well-formed formula phi which is true under some truth assignment, then we'll regard not phi as being false under that truth assignment, and if phi is false under that truth assignment, we'll regard not phi as being true under that truth assignment. And as usual, we make not into a logical operator following the rows of that table, so we'll regard not true as being false, and we'll regard not false as being true. Okay, and the final example then is the final connective that we've not yet dealt with is the connective implies. So here is the truth table defining our interpretation of the connective implies. And this one is perhaps a little bit more confusing. People often find the truth table for implies a little bit counterintuitive or difficult to understand the way in which it corresponds to the ordinary use of the connective implies. So rather than talk about that for a long time in this video, I've included a little bit of discussion and a couple of links by the Fields medalist Tim Gowers in the online notes or in the lecture notes for this section of Math 5. So I'd really suggest that you have a look at those and read them. But just in brief, to give truth values to the well-formed formula phi implies psi once we've got truth values for phi and psi under some truth assignment. Perhaps the easiest way to think of a sensible definition for doing that is to think, what would it mean for that implies statement to be false? Well, usually the only way in which phi implies psi could be false is if phi were true but psi were false. That would be a statement in which it would be natural for that to be regarded as false. So that corresponds to the row of the truth table just here. So when phi is true and psi false under some truth assignment, then we'll make phi implies psi false. And in all other cases, we're going to regard the implies statement as being true. So as I say, if you find that a little strange, then my main recommendation is to have a read of those notes and maybe come to office hours and ask about it then. But just to complete this video, as for the other connectives, we make implies into a logical operator, which means that if you see true implies true, we'll regard that as true. Second row, if you see true implies false, that's going to be false. But in all other cases, so false implies true and false implies false, we will regard both of those things as true. And that's great. Now we know how to use all of our connectives as logical operators as well as to form well-formed formulas. So we're now ready to start giving truth values to all well-formed formulas.